So I asked for a little bit of time at this meeting to discuss an idea that I had that emerged only in the last 3 weeks. And as the title indicates, it's an investigation into whether origins can serve as a useful node in the Event Horizon Telescope. And I want to emphasize that this is a work in progress. But let me remind you that for those who haven't read the headlines when this incredible image was made public, that the Event Horizon Telescope, as it consisted at the time that image was made, involved 8 observatories spread across the Earth. I think I'm right, Dom, that the solid lines denote the observatories that were used to make that image.
That's right. There was lots of visibility down 87.
Right. And the others were for SAG-A. One of the nodes in the Event Horizon Telescope is the Smithsonian Submillimeter Array, which consists of 8 6-meter diameter antennas located on Mauna Kea. And I'd remind you for scale that each one of these antennas is roughly origins. So the question is, origins with heterodyne capability perhaps can serve as a node in the evolving version of the Event Horizon Telescope. Let me remind you what advantage this would bring, and Dom is going to put a lot more meat on the bones. But right now, the Event Horizon Telescope synthesizes an observatory roughly the size of the diameter of the Earth. Adding origins to the Event Horizon Telescope would offer more than 100-fold gain in angular resolution. Specifically, right now, and Dom, you can correct me if I'm wrong, the spatial resolution, at least involved in the spectacular M87 image, was about 25 microarcseconds. With the addition of origins, that could bring it down to about 0.17 microarcseconds. And if you think in terms of linear distance, the linear spatial scale at M87 was about 400 AU. With origins, we could reduce that to under 3 AU. Now, one of the questions about introducing another node in a telescope is the UV plane coverage. So I just wanted to remind us that for an object located at the ecliptic pole, there's very limited UV plane coverage. You basically have a single baseline, and it's constant at about 1 million miles. The distance between the Earth and L2 in miles. For an object in the ecliptic plane, however, at one point, the object and the Earth will be 1 million miles apart. But if you wait 3 months in the ecliptic plane, they sit on top of each other and the baseline is 0. So you basically, for a source at the ecliptic plane, cover all baselines between 1 million miles and 0 miles. And more generally, for an object at an angle above the ecliptic plane, which I denote as E latitude, ecliptic latitude, it goes as the sine of that value. Turns out M87 is 14 degrees above the ecliptic plane. Interestingly enough, 3C 273, the brightest quasar in the sky, is about, I think it's about 7 degrees above the ecliptic plane. So this is sort of the overview. Dom is going to talk about specifically what science gains there would be in adding origins to the Event Horizon Telescope. And I will come back and close with the modifications to origins that would be needed in order to enable this.
All right, thanks, Gary. I think, oh, great, it went right to this one. So like Gary said, I'm going to primarily try and focus on the science, some of the science that we've just really barely started thinking about that could potentially come from extending millimeter VLBI or submillimeter VLBI to these extremely long baselines, such as that L2 with origins. So I think Gary gave this great intro. It's going to be a little bit redundant here. I'll try and go through it pretty quickly, but just as a recap, everybody already knows, the Event Horizon Telescope project recently published an image of the horizon scale emission around the black hole in M87. And this great little video here just shows a zoom in on that galaxy to give you a sense of the scales that we're really going into. So it starts, you see the radial lobes around the galaxy here in red, and it's going to pass through the Hubble stellar emission, and you can see the relativistic jet, and then it zooms in. You can see traditional VLBI images of that jet, and it goes in further, and you see what's considered to be high frequency VLBI, and then it goes further into the millimeter VLBI that the Event Horizon Telescope image is taken in. And so the spatial scale of this image is about 40. The diameter of this ring is about 40 microarc seconds in size. It's one of the smallest angular scales ever imaged in astronomy, and possibly the smallest ever actually imaged, and maybe just one of the smallest ever probed in any variety. And you saw this plot already. This is in 2017 EHT Array. This is responsible for the observations. 8 sites at 6 distinct geographic locations. Only 7 of them had visibility to M87 in 2017. The South Pole Telescope can't see anything in the Northern Hemisphere, but is very important for observations of the other primary science target, which is Sagittarius star. But a sort of just necessarily true thing about all these VLBI arrays is they're very sparse, right? So we have baselines that are about an Earth diameter across, and there's just no way to fill that in densely, right? You'd have to fill in the whole Earth. With telescopes, it's not feasible. And so the sort of idea that we had been playing with as far as moving things into space had primarily been my apologies. First, just a brief recap of how Earth aperture synthesis here works. So we have a sparse array, and we rely heavily on the fact that the Earth can rotate and fill in the Fourier spacings a bit for us, right? So here on the left is the view of the Earth as seen from M87, and this is an animation where you're just watching it turn. Telescopes are coming into view, and you can see the baseline orientations and projected lengths change with respect to the source, and then the points on the right here, these little tracks that those baselines trace out. Just a reminder that in interferometry, we sample the Fourier transform of the image. This is the sort of typical radio astronomer's UV plane, U being the east-west spatial frequency, V being the north-south spatial frequency, and so trying to flesh that out a little bit, this Earth rotation aperture synthesis is pretty critical, and it takes a while, right? The Earth takes several hours to rotate substantially, and this is really where we'd been mostly thinking about trying to push to space. We'd been primarily interested in trying to push to low Earth orbit, because if you have just a single snapshot of something like an observation of Sagittarius A star is up in the top right there, you really don't get very much coverage in a single snapshot. And even if you wait a few minutes, and so here's an animation that's going to play showing on the top typical, and on the bottom one with a low Earth orbiter that has a 90-minute period around the Earth going around. You can see that the UV plane gets filled in both much more thoroughly and much more rapidly when you have even a single object in orbit. And this is critical for an object like Sagittarius A star. If you want to actually make images, the timescale, the dynamical timescale of that system is really on the order of minutes. And so we don't have time to wait for the Earth to rotate over the course of an observing track. Having something like this that can fill in a substantial fraction of the UV plane in a much shorter time is pretty critical. And this is really what we'd been thinking of when we thought of extending millimeter VLBI into space. We were thinking low Earth orbit. Let's get that UV coverage, and that will be great for Sagittarius A star if we can get something like that. But a few weeks ago, Gary came up to us and was like, well, what about L2? And the one thing that low Earth orbit doesn't get you is resolution. You basically have the same length diameters as you have on the surface of the Earth. Low Earth orbit's only maybe a few hundred kilometers at best above the surface. You basically still have Earth diameter resolution. But pushing out beyond low Earth orbit to GEO or beyond to L2 is where you really start to think about some serious resolution gains. And so here is now that same on the left UV plot looking at M87 again with maybe one night's worth of observing or one day's worth of observing from the ground-based sites. And then on the right is a comparable track over the course of a year observing M87 with a baseline from Earth to L2 at 230 gigahertz. And this elliptical track is what you would see if you observed it once a week. So there's 52 dots on there. And you get an ellipse because, as Gary said, M87 is at an ecliptic latitude of about 14 degrees, which means the projected baselines vary between 1 and 1/4 times the 1.5 million kilometer distance from Earth to L2. But the scale here, you can see I've drawn a circle corresponding to, on the left, a 25 microarcsecond fringe spacing, and on the right, 100 times smaller than that. We're really accessing spatial scales that are enormously smaller, right? Like more than 100 times smaller than what the EHT can currently see from the ground. And you can even think of doing a little bit better if you push to slightly higher frequency, which is actually, something like 345 or 690 gigahertz, which are considered to be quite difficult from the ground. Only a few sites can really access these frequencies, ALMA being the sort of prototypical example of a site that actually, in good weather, can observe at these frequencies. Would be something like bread and butter for origins, right? There's no problem observing at a frequency of 690 gigahertz. And so you could potentially even think about improving the resolution by another factor of 2 or 3 just by bumping up in frequency. And so you're talking about somewhere between 2 and 3 orders of magnitude increase in the resolution that you have access to. So the natural question is, what is the science that can be accessed from this? Right? We don't have a ton of UV coverage, but we do have a ton of resolution. What can we do? And so to take a step back, I think I first want to address, well, what can we do with resolution like the EHTs, right? What is the sort of thing we can do? And so here I'm showing a one-dimensional version of that UV plot. So now it's just basically the 1D Fourier transform of that image in the upper right there. So the green is the sort of azimuthally aggregated Fourier transform of this simulated image of an M87-like black hole, about 40 microarcseconds in diameter. The red points are samples from, simulated samples from the EHT 2017 configuration. And the critical thing that I really want to get across here is that this Fourier transform of a ring looks something like a Bessel function. And in order to really, what I mean by resolve it, you want to spatially resolve this ring in terms of the Fourier transform. That means you want to have baselines that get you past that first bump, right? You want to get past that first bump so that you can measure the diameter of the thing. The diameter of this thing is I don't know if we're taking questions in the middle or if we're waiting until the end, but so yeah, why don't you give you a question, please?
It's 100 millijanskis.
Yeah, so the compact flux density of M87 is about 500 millijanskis. So this is totally meant to be pretty realistic. Yeah, this is the extended flux density is much higher, but at these spatial scales, it's about half a Jansky.
So I had a question too about this. The problem is all surface brightness.
Yeah, so definitely, if you wait a few slides, that'll be a very key topic.
What's the bandwidth that you can send down? I mean, that's
so I'm primarily going to focus on the science discussion here, and then I think the technological capabilities will have to follow that. I think I just want to get through this material.
Well, currently the EHT gets its bandwidth by flying hard drives around the Earth.
That's right.
Oh, okay.
I'll talk.
Not great, but I just want to understand this observation. So you have to go longer than 8, actually 10. You need longer than 10 gigalambda.
So longer than 10 gigalambda for.
To get, when you say see past the first visibility.
Sorry, the first visibility. So this maybe I should say the first null here, right? So this is EHT style coverage, and the EHT does resolve this ring. So this is sort of the image of like what you would see for this coverage of this source. And so what I wanted to show was just this sort of thing you can see. And now I see people are already thinking about flux density, so I'll just ask that you hold off one moment on flux density. I'm going to talk about resolution first, and then I'll get to flux density. Because if you push this object 100 times smaller, you zoom this thing way out, and you say, what about this object, but 100 times smaller? And you ask, what do the L2, the baselines from Earth to L2 cover? Well, they cover that bit over there, and you see that coverage looks a lot like, this was over the course of a year. This is the same UV coverage I showed earlier, but that plot looks a lot like what the EHT can currently do for M87. So we would expect to see a comparable result in terms of diameter measurement, right, which corresponds to mass measurement here, or mass to distance ratio more precisely. For an object, of order 100 times smaller in angular size than the M87 black hole with this level of resolution. And the thing is, there's an awful lot of these objects, right? Like there is about the volume you have access to goes as something like the length of your baseline cubed. And so if we have one M87 type object for Earth-sized baselines, if you expand them by a factor of 100, you're talking about something on the order of 1 million black holes with angular sizes of this size or larger. And so it's just a vast increase in the number of potential targets that you would have access to. And something that I think maybe even a little bit cooler than that is that the angular diameter distance turns over at about z of 2. So if you can resolve an object spatially at z of 2, you can resolve it at any redshift. And so this actually means that for black holes of order 10 to the 9 solar masses and larger, baselines to L2 could resolve them across all of cosmic history. The spatial resolution doesn't need to be any better than that for any redshift. So that's something that sort of we just realized kind of recently, and it just sort of fascinated me. The prospects for that sort of capability. But you don't just need to look at smaller things, smaller black holes or an angular size. You could also think about pointing this thing at the big ones and looking at finer structure in those, right? So M87 is still going to be 40 microarc seconds, even if you have a resolution 100 times better than that. So what is M87's Fourier transform if you were to just continue this out there? It still has some power at those high spatial frequencies. And if the image there has now just been increased in resolution by a factor of 100. And this is just looking at some of the finer structure there that we could see if we had something like a factor of 100 better resolution. So this bright photon ring becomes immediately evident, and you can really see the first subring there on the inner edge, this sharp bright feature, and sharp features in the image domain correspond to these ringing features in the Fourier domain. And so without getting into too much detail, this is a project being led now by Michael Johnson at the CFA. There's an awful lot of information contained in these higher frequency bumps and wiggles. So things like the separations of these bumps give very accurate, very precise measurements of the diameter along a particular orientation by comparing these things along separate or orthogonal orientations. These would just be very precise probes of the shape of the shadow and therefore the black hole spin and the Kerr metric in general. So just the kinds of science here, it seems to be really incredible, but as people have already really started to point out, there's a really critical problem, probably comparably challenging to actually getting something like this to work, would be being able to detect something there. So the sensitivity limits that you run into are extreme. In all the plots I've shown, you haven't seen anything at these long baselines peaking up, much above a millijansky, and probably much less than that. And so that comes from a fundamental physical limit primarily. Most of these things are emitting synchrotron radiation. There's a brightness temperature limit to that. We don't think it can exceed 10 to the 12 Kelvin. In many cases, it might not even be able to exceed 10 to the 10 Kelvin. And so in this plot here, those limits are shown as diagonal lines. So this is a plot of the flux density expected for a source versus the shadow diameter you would expect it to have. And L2 is the range of baselines corresponding to the L2 Earth baselines are there in the top in a purple box. And so the region in red, or in gray there rather, is where we would expect to see no sources at all. They would exceed this physical brightness temperature limit. In this purple box is sort of what you might expect to get for a level of bandwidth that we have access to sort of right now, and an hour-long integration time on a baseline from Earth to the Origins telescope at L2 with a 5.9 meter diameter. And again, you really see that at the baseline length or shadow diameter corresponding to the L2 baselines, you're really not going to see anything above a millijansky just because of this brightness temperature limit. So that's that really is going to be the big challenge to ever making something like this work. And overcoming this challenge is not going to come from increasing the telescope area, right? Because Origins is going to have a fixed diameter. So we're talking about something like bandwidth or integration time improvements. And the equation to have in mind here is this one. Really, you want the time bandwidth product to be as large as possible. There may be some finagling of the individual telescope sensitivities. If you made ALMA bigger, for instance, you could maybe drop that SEFD a little bit. But primarily, you're gonna be talking about increasing the integration time, increasing the bandwidth. There are a number of, I think, technical things that could be talked about here. I think Gary is going to get to some of these. I'll just keep it to the science and move to the summary slide. So the takeaway that I really want to leave you with here is that these resolutions are kind of just completely unprecedented, and we've only really just started thinking about them. But some of the science we've come up with so far seems really exciting if it's actually accessible. So this, being able to measure masses for millions of black holes, being able to measure the cosmic history, the evolution of black holes, at any redshift, and being able to really study the fine detail, the photon ring substructure that nets you really precise measurements of some of these general relativistic quantities that we really don't have access to in other ways. These are all really exciting topics, and the cost, of course, The catch is that they come with the requirement that you have a really sensitive baseline, and overcoming that is going to be a big challenge. So I do want to be forthright about that, but I think the science is rather compelling, and hopefully other people would agree. Please.
Said that,
Yeah, so if you have a black hole of a particular mass, that corresponds to a particular. I can go back to that slide. That corresponds to a particular physical size of the black hole shadow, right? And so if you put that further and further away, you'd expect it to just get smaller and smaller. Yes, but actually the universe has been expanding, right? So the relevant distance metric to determine the angular size of an object of a given physical size is the angular diameter distance. And the angular diameter distance in our universe's history has a maximum. Its maximum's a z of a little bit less than 2. And so actually things only get so small.
okay,
They get really faint,
yeah.
but they only get so small.
Okay.
What'd you say? Yeah, well, there's SCFD considerations. So this is all very, very, in its infancy in terms of this really needs to be fleshed out considerably more. The SCFD could help us. You know what I mean? And that's a separate consideration.
Yeah, but black holes are
Yeah, okay.
less massive and smaller.
Well, not only that. Why is it interesting? I mean, the event horizon. There is no time. There's no time dependability. So it might sound cool to observe a black hole at a redshift of 2, but what do you scientifically gain over observing a low?
So what I think you gain. So for instance, we know that black holes have had to grow, right? So the thing I envision is something like observing black holes through a range of redshifts. Right, and watching something like the distributions of these masses changing, get something like the black hole mass function as a function of time. Maybe you'll see which galaxies they're in. You'll learn something about their environments, and I just think it's something like a direct handle on black holes, the likes of which we currently just don't have, and then how they evolve in a truly cosmological timescale. I think is currently unacceptable. This is another avenue that I had only just before a few minutes before this talk even considered, but the gravitational wave connection is something that could also be super exciting. Please, yeah, if you have a question.
Yeah. Well, so my main question, my main concern would be the following. I mean, when you look at the EHT observations and just look, for example, at a telescope that did not work so perfectly, which was the LMT, I know how much trouble it was to get any fringes out of that. And the main reason was calibration and pointing accuracy issues, right? So if you the plots that you showed us that we need to go 4 orders of magnitude lower fluxes. So I don't think the theoretical expectations in the ideal world are now what you have to consider, but realistic. There must be higher order effects in the measurements of amplitudes and phases from ground-based observatories, including ALMA, which my first guess would be completely preclude you to ever get down to those sensitivity levels.
Or sub-millijansky, they aren't unprecedented for connected element arrays at all. So things like the VLA and ALMA routinely go well below this flux limit. Millijansky continuum source is no problem for the VLA or even for ALMA. The issue here is that we're connecting with a space telescope that's much smaller, and you get the geometric mean of the collecting areas as your sensitivity here. So I think you're talking about problems that maybe arise when you have signal to noise of 10,000 or 100,000. But I think we're aiming for signal to noise of 10 or something here. Maybe I'm misunderstanding your question. But I mean, Millijansky level flux is not sort of in an absolute sense something ludicrous.
Well, for VLBI, I think it still is. I mean, you're talking about very small baselines and things where they really have phase references, etc. But you can't achieve that in this type of.
We have not yet achieved it. These are sensitivities that are at least an order of magnitude lower than the sensitivities we have achieved with the EHT so far. That's right. So order of a few millijanskys, probably more like 10 millijanskys, are our weakest detections with the EHT so far. But pushing that by an order of magnitude or 2, that is the challenge for sure. I think there was a hand over here first, I think.
Yeah, so
Sure. Yeah, if you didn't have a sharp, if you didn't have a series of sharp photon rings like I showed in that zoomed in image, yeah, without sharp features, you don't have power at large baselines. Yeah, absolutely. This is the case. The case is you expect the photon ring to be self-similar in nature with these increasing. It's actually a beautiful result. Michael Johnson is going to. I know I'm running out of time here.
Yeah, yeah, no, we'll take Karen's question and then Gary.
Mhm. Well, that was basically what I did for these sensitivity calculations. I assumed you could phased up ALMA like we do for the EHT, and you just kind of yeah. Oh, no, there's super big concerns. Absolutely, yeah. ALMA phasing right now. ALMA doesn't phase up on any source weaker than like half a Jansky right now. So yeah, no, I mean there's loads of difficulty involved in actually implementing this in real life. Yeah. Yeah, you would need to give ALMA wider bandwidth, so you'd need to do all sorts of things. Absolutely. Yeah. This is what I mean. Like by
Okay,
2030.
let's move on to Gary doing a few technical things, and then we have to break up into small groups. But we're going to start with Alex Lockwood, going to just maybe give talking points about how to pitch a great origins talk. Do you want to?
Yeah, okay. So let me just make clear that the intent of this presentation is to introduce a new idea. It is not to, in any substantial way, change our report. I mean, at most, what we would be arguing for would be to mention this as a possibility that is worth studying further. And the EHT folks have committed to working hard on this over the next few months to flesh this out. So I'm going to present a list of technical challenges to implementing this, but don't think for a moment that I'm suggesting changing our baseline. So one of the things we would need to do, of course, we would have to invoke the upscope that includes HERO and add a single pixel at 230 and 345 gigahertz to correspond with the ground-based sites. Fortunately, these receivers exist. That's what was used to take the data that we saw, and they operate near the quantum limit. So this is not a particularly high hurdle to cross. Onboard storage, the data generation rate used by the EHT in the image that we saw was between about 150 and 200 gigabits per second. So we have one of two options. One is to carry enough onboard storage to store the data and downlink it over time, or if it's technically feasible, downlink the data in real time. Currently, spacecraft have launched with memory of a few terabytes. We would need between 500 and 1,000 terabytes to record a 12-hour observation. But if you assume, space qualified memory doubles every 18 months, then you're at about 500 terabytes in the 2030 timeframe. Now, this is, of course, scalable. So even if you only are at half that amount, you fly twice as much memory. And that would be a weight and power issue, but it's not a technical issue. Yeah.
Quick question. That seems like a lot of data for a single baseline. Can't you just compress all the data? I mean, all you're looking for is one number, amplitude and phase.
This comes from the bandwidth requirements.
So, but just compress it.
Sensitivity. Right? You need to have such an enormous amount of bandwidth integrate over a long time.
But you don't need to record every channel.
Yes, you do.
Why?
Very fast.
Why?
Because you're looking at the voltage and you're looking for the cross correlations. The signal has to be able to change very fast, so you have to record it fast. And if it doesn't change very fast, you don't have the bandwidth, don't have the sensitivity.
Okay, maybe we'll do this offline.
Okay.
Just given that very high, given our laser, or however we're going to use for a downlink, how long will it take to downlink?
Well, that's the next thing here. We've spoken to people in the communications group at Goddard, and John Ehrenberg is going to check this independently. But they say that in the time frame of 2035, which is when we'd be downlinking these data at the earliest, downlink rates from L2 of 100 gigabits per second, they regard as feasible. as one can claim it without being thought insane. And I believe John was saying, and the Goddard folks were saying, there have been demonstrations of 10 or more gigabits per second already. So in 15 or 16 years at the earliest, people believe that this will be feasible. If it gets much better than that, then it may be possible to downlink the data in real time, which would reduce the onboard storage requirements. If you can downlink the data in real time, you don't need to store it. Lastly, you need a good clock with an accuracy better than 1 part in 10 to the 15. But I would remind folks that on June 22nd, NASA will launch something called the Deep Space Atomic Clock, which is about 11 inches by 11 inches by 9 inches, roughly like a toaster oven, with an accuracy of 3 parts in 10 to the 14. So nobody I've spoken with yet regards 1 part in 10 to the 15 as something that would cause people heartburn in 16 years' time. So again, these are the technical tall poles, with the exception of the first one, that I think we would mention in an insert as being necessary to enable origins as a node in the Event Horizon Telescope, and hopefully we can add a paragraph with each of these that show that in the time frame of this mission it's feasible.